I'm here to talk about Miniscript, which is a project I've been working on for the last year or so with Peter Wola and Sanjit Kangalkar. Miniscript is it's a thing that's on Bitcoin. It's a thing you can use today on the Bitcoin blockchain. So if you want to use it, you're welcome to, and you can. There's not really a whole lot more. Well, I'll talk about how to use it, and I'll talk about a few open research problems. But most of the problems Miniscript solves, I'm happy to say we've kind of wrapped up and can walk away from, which doesn't always happen in research. Sometimes things just stay in your life forever. All right, so we're kind of whittling down to the diehards here, but let me remind everyone how Bitcoin works real quick. And I'm going to describe a bit of Bitcoin script. We heard from Oleg and Russell some bad things about script, and I'm going to try to demonstrate some of those bad things. So first off, the state of the Bitcoin network is basically there's this giant set of UTXOs, unspent transaction outputs, that all the validators see. Whenever they see a transaction spends some UTXOs, it creates some new UTXOs, and basically it does a diff on the UTXO set. And there are some extra conditions, of course, that need to be validated to do this, but at a high level, that's what's going on, okay? So every UTXO has kind of this ID thing here that's on the left. You can see this giant hash that I've cut off, and then a number. And the hash represents the transaction that the output was created in. The number is just which output of that transaction it was, starting from 0, 0, 1, 2, 3. Okay, and every UTXO has an amount. This is where the coins are. They're on the UTXOs. And something called a witness program. Okay, and a witness program is what we usually think of when we're talking about Bitcoin. We usually talk about all the coins having keys associated to them. You sign with these keys. It's actually a fair bit more general than keys. There's actually this program in this language called Bitcoin script. And the term we use for this program is witness program. And this is to contrast from earlier versions or the original design of Bitcoin transactions, where the distinction between witness data and programs and signatures and stuff like this was kind of murky. Russell talked a bit about how originally there were two scripts, and you would execute one and then the other, and this was going to be the spending model. And we don't, I mean, the network still supports this because the network still supports everything, but you don't need to know that anymore. Of an amount and a witness program. Okay. Transactions destroy, they reference some old UTXOs, they create new UTXOs. Okay, so here's a one input, one output transaction. It's just exactly what I said. To spend a UTXO, you provide some extra data called a witness. Typically, this includes an ECDSA transaction or something. And what this witness is some data that you run through the witness program. The witness program says yeah or no. And if it says yes, the transaction is valid. If it says no, then it's not. Okay, then the transaction just can't go in the blockchain. All right, so I'm going to jump right into what Bitcoin script looks like. I'm going to play through this script. So on the right-hand side here, and just to preface, if you're familiar with Bitcoin scripts, you might learn some new weirdness here. If you're not familiar with Bitcoin scripts, the only takeaway here is that it's just frightening and weird and unnecessarily complicated. So I'm kind of deliberately going to go too fast here to try to sell the emotional message about Bitcoin script that I want to. So on the right, I've got this script, okay? This is actually this weird, one of two threshold signatures. So the idea is this script will allow you to spend coins either by providing a signature with this pub key PK1 or a signature with PK2, okay? And I've got on the left-hand side, I'm going to play out those two scenarios. So on the far left there, I'm going to use a signature with PK2, sig2. On the right, I'm going to use a signature with PK1. Okay, and what I've drawn here are actually the stacks. So Bitcoin script has a stack that it operates. It actually has two stacks. The other one's not really good for anything. It's a stack machine. It's a series of opcodes. All these opcodes manipulate data on the stack or manipulate the stack itself in some way. So let's play this forward, okay? So the first, so starting out, the top thing on the stack is this thing called a witness script. The witness script is the same as a witness program. The witness program is a commitment to the witness script. And that's just a technicality. I don't think there's any semantic forget about that. It's just a notational thing. But the first thing on the stack is actually the script, okay? When you're spending coins, you have to reveal the script because originally there was only a commitment, okay? So let's start executing the script. We eat the script, we parse it, we check the hash matches, all that good stuff. First opcode we encounter is this thing ifed up. This is a single opcode. If you give it something that's non-zero, then it will duplicate it, okay? If you give it something that's 0, it will not duplicate it. There's the effect of executing ifed up. Next opcode is not. Not is kind of what you expect. It turns anything that's 0 into 1. It turns anything that's not 0 into 0. So you see, I've on the left playback, I've duplicated my signature, and I've turned the signature into a 0 now. On the other evaluation, I started with a 0, and I turned it into a 1, okay? And then I run the one add opcode. That just adds 1 to something, okay? Then I'm going to put the public keys on the stack. Now I have this other opcode toSwap. This takes the top 2 elements and the 2 elements below it and changes their order, okay? And now I'm going to execute this opcode oproll. What roll does is it takes this top stack element, it interprets it as a number, it indexes that number into the stack. You see on the left side we're looking at, and from 0, we're looking at the first element on the left and the second element on the right. And then it brings that element to the top of the stack. It moves it, okay? So now you can see I've got a public key and a signature at the top of both stacks, and I've got the right public key, or I've got the right signature for the right key, okay? And now I can use this checksig operator, which actually does a signature check. If they pass, it'll give me 1. If it doesn't, it'll give me 0. And then finally, I call this opcode nip, and nip deletes the second to last, or the second to the top stack element to get rid of those public keys that were straggling, okay? So suppose you are just trying to run a business, and you have to deal with Bitcoin for some reason, and one of your engineers comes to you with a script, and it's like, you can use one of these two keys, promise, and maybe they stick like a time lock somewhere in there, so one of them's only useful in an emergency or something like that. How can you reason about this script? Well, it's only like, what is that, 8, 3, 5, 9 opcodes. I mean, you can kind of like grind through it. You can play through this and convince yourself that this script is actually okay, that it actually does what you expect it to. I mean, maybe you can. I spent a while trying to convince myself this is legit, and I'm not certain. So let me just give a quick highlight of the weirdness of each of these opcodes. Or just a couple. First off, not. I mentioned not turns 0 into 1, and it turns non-zero into 0. It's not really true. So the way that not interprets whether something is 0 or non-zero is any string, and any object on the stack, which has only 0 bits in its whole representation, that counts as 0. It doesn't matter whether it's empty, it doesn't matter whether it's a single 0 byte, it doesn't matter whether it's like 50 0 bytes, okay? It's 0. Also, if the very highest bit is 1, so you have like a hex 80 and then all zeros, that's also 0. That's negative 0. This doesn't, so Bitcoin has a notion of negative 0, by the way. This is different from that, because all the uses of numbers in Bitcoin are limited to 4 bytes. But the way that not works and the way that if works and not if and all those, they take Booleans, which have this notion of like extended zeros, basically. So the extended negative zeros that you've got to worry about. And there's actually a vulnerability if you were to try to deploy this on the blockchain. And that vulnerability is, suppose that somebody tries to spend with a second signature. You remember we started with a 0 on the stack. Well, anyone can take your transaction, replace that 0 with a much larger 0. Now your transaction has a higher weight. The fee that you put on that transaction is no longer paying for as much transaction as you thought that it would. And now your transaction is going to sink to the bottom of the mempool, or maybe it won't be relayed, or some other bad consequences like that. And let's see. So if you wanted to fix that, there's kind of a cool trick. And I'll tell you that, and then I'm just going to move away from Bitcoin script for the rest of the talk. You can use the size equal verify. There's 2 opcodes there. Size takes the number of bytes that something is, that a stack element is. Equal verify checks the 2 things are equal. So size equal verify. If you run that on the empty string, the size is 0, which is also the empty string, and equal verify will pass, right? Empty is empty. If you give it 1, the size of 1 is 1, so it will pass. If you give it anything else, the size of the object will be different from the object itself. And so you can actually force, if you need actually 0 or 1, size equal verify will force it for you. That's the kind of thing that you need to know to do basic things like using an if statement in Bitcoin script. You need to know this extra safety catch to make sure your transactions aren't vulnerable, okay? Everything in script is like this. Arbitrary, just random arbitrary limits in like every direction, every time you turn. There's a limit on how large your stack elements can be, how many stack elements you're allowed to have. There's a limit on how many opcodes are allowed to be in your script. For some reason, if you execute a multi-sig opcode, the keys count as opcodes. But if you don't execute it, then they don't count. So it's actually the number of opcodes in your script plus the number of keys that get used in a check multi-sig opcode, which is executed. Okay? There's that quantity. That's limited. It's 201. You need to know that. There are limits to how many signature operations you're allowed to use. And so even if you can get through this multi-dimensional constraint problem, you still need to do a bunch of estimation and analysis on this to do things like estimate fees. Okay, so I'm gonna jump ahead, and basically, here's a quick summary of what I just said. Well, okay, I've been talking about edge case behavior, but on a higher level, the problem with Bitcoin script is that the script model does not correspond to the user model. Okay? When you're writing Bitcoin script, you are not thinking like, oh, I've got a bunch of blobs in a stack. I want to rearrange these blobs in a certain way. You're probably thinking in terms of spending conditions, in terms of keys to sign, in terms of time locks, in terms of revealing secrets or chaining HTLCs off each other or whatever you're doing. And in order to implement this, you have to somehow translate your problem into Bitcoin script. You have to somehow convince yourself that script is not doing something awful and surprising. And it is. It always is. I've been working on Bitcoin. I've been using Bitcoin scripts for 6 years, and I still I've learned new stuff in putting this talk together. It's very weird. And even if you can do this, how do you verify that you've done it right? Right? How do you get this mapping between? How can you deal with the fact that what you put on the blockchain and what you want the blockchain to do are just completely different languages? Here's a quick summary of practical issues. So I've been talking about arguing correctness and security. That's obviously important. Does the script do what you expect and not do things you don't expect? There's also, in practice, difficulties with scripts. You need to know how large your witnesses will be. In order to put a fee on your transaction, you need to know what's the worst case. And if you've got some big multi-signature weird script, maybe there are other parties participating, you need to know what's the worst case. What is the worst set of keys that would cause the largest possible satisfaction? How can I pay enough fees for that? That's a hard question to answer in general. Even if you can tell which signatures are needed, which is difficult, you may have seen in the script that I ran, it's not like you can just look for the checksig operator and see what came before it. There I had 2 public keys, 1 checksig. Try to automatically extract public keys there. And then even if you can figure out which signatures you need, once you have them, how do you use them, right? In the example script I gave, if you're signing with pub key 1, you put the signature on the stack. If you're signing with pub key 2, you have to put the 0 on the stack, and then your signature. And also you need to do this size equal verify guard, which wasn't in the script, so actually you'd be screwed. So I guess what you should do in that case is assume that somebody's going to put a 520 byte 0, which is the largest allowed 0. Or it might be limited to 4 bytes. I need to check my table of which opcodes have which byte size limits. But you just find the maximum, pay for the maximum. That's life. You need to know all the maximums. Okay, so there's a lot of things people want to use Bitcoin for. We've been talking in the Bitcoin world. We've been telling people that we have this script system. You can do all this cool stuff. You can do arbitrary monotone functions of signatures. You can do signature checks. You can do time locks. You can do hash preimages. We build cool protocols, HTLCs, stuff like this, using Bitcoin script. But in practice, it's just a real nightmare to use. And everybody winds up having to write their own ad hoc code to answer all of the questions I just posed. And the result is a lot of wasted and duplicated effort and a whole bunch of wallets that do very little and don't interoperate with each other. Okay? So the idea behind Miniscript is we are going to take script. We're going to find templates for like really basic operations and build a better language out of those templates. Okay? And what we've done is we found 26 fragments. They're all like very straightforward. Like a couple of them, one of them is like 1. It puts a 1 on the stack. Another is like a check sig operator. It checks a signature. Some of them are a little bit more involved, but they're all like very basic, primitive things. And we can compose these. So you can build a set of sending conditions out of these new primitives that have much clearer semantics and that allow you to answer all of these logistical questions in a much more straightforward way. So as an example, on the right here, I've got a Miniscript, which I've represented here as a tree, as a colorful tree. You can serialize this, of course, as a string, as a standard serialization, but I wanted to draw pictures. On the left is what this looks like in Bitcoin script. You can sort of, maybe you can see what's going on, because I indented it nicely and added some color. On the right is the Miniscript. You can see there's some noise there, right? You've got these little subscripts like B's and V's and stuff. You've got like or sub D. What is that? What is that sub D? And then you've got like these things with colons in there. All that noise basically represents how this is encoded in script. But none of the noise matters semantically. Okay. So what is this policy? Here we have at the top level we have an or. We have a choice between two things. On the left side is a thresh M, a multi-signature, a 2 of 3 multi-sig. On the right-hand side, I have a conjunction. I have an and of a emergency pub key and a condition older 1,000. This thing has to be older than 1,000 blocks. So what this is are coins that can be spent by 2 of 3 participants, but if they don't move in 1,000 blocks, then this alternate branch appears, suddenly becomes active, and this emergency pub key is able to spend them. Okay, and you can sort of see that visually. Like you probably didn't even need it. If you were aware of what script could do, you probably didn't need my exposition here, unlike with the script itself. All right, I'm going to skip over this slide. I was going to explain a little bit about what all the different noise components mean, but it's not too important. There's a website that I'll link at the end that explains it in great detail. But let me show you a larger example and quickly run through the kind of things that you might do with Miniscript. So here I've got like a much larger script. At the bottom I've got the actual script encoding. You can ignore that. At the top I've got this the Miniscript, like the actual Miniscript. And so the first thing I'm going to do if I'm trying to reason about this, I'm going to throw away all the noise. Okay? That's very easy. It's like well-defined what's noise and what's not. Unlike in script where everything is both noise and semantically important. Here I just throw away all the subscripts, everything before the colon and stuff, and now I've just got this abstract tree. And so suppose I own pubkey 4 in the bottom right here. And my job is to be a countersigner. I'm some company like BitGo or like Blockstream's Green Wallet or whatever, and I'm supposed to provide some sort of countersigning service. And all the rest of this, so I control PK4, all the rest of this script I really don't care about. That's my customer's problem. That's like whatever customer logic there is. Okay, all I want to know is basically, given this script that my customer has given me, I want to ensure that I am necessary for these coins to move, okay? And if I'm necessary, then I'm a cosigner. That's my job. Good, I'll take it. If I'm not, if there's some way you can spend the coins without me, then I'm going to say no, like you're violating the terms of this. And you can see this is true. So you can chain through. At the top level, I've got an and. I need both of those. On the right, I've got an and. I need both of those. And on the far right, I have a choice between either signing with my key or a 1,000 block timeout. So I can look at this. I can immediately say, there is no way to spend coins encumbered by this script unless either I sign or there's a 1,000 block timeout. That's what I want to see. And I don't even really need to look at the rest of the script. So I can run through all the different possible spending conditions basically and check that I'm involved in all of them. All admissible sets of signers I'm involved in. Okay? And then what's cool is I can go the other direction. I threw away a bunch of noise to get this. Given this policy, I'm going to call this a policy now, it's possible for me to reinsert the noise in the most efficient way. So I have many different choices for how I can embed this in script. Script has many ways to do ors, it has many ways to do ands, it has many ways to do all sorts of stuff. What's the optimal choice? Peter Willa and Sanket Kanzulkar wrote compilers for this policy language. The policy language looks basically like this. It's Miniscript without the subsets that will just exhaustively try all the different possibilities and come up with the most efficient script representation given some information you feed it about what branches are more likely and which branches are less likely. So it's often the case that if you have a likely branch, a branch that's likely to be taken, you can optimize to make the witnesses for that small at the expense of making the witnesses for unlikely branches very large. And that's what you want to do in general. If something's unlikely to be taken, then you want to optimize for its program size and optimize against its witness size, because you're never going to provide a witness. So who cares how large they are? And that's the sort of thing that our compiler is able to do. Okay? And then also, I don't have my list of things, but all the logistical things I mentioned, things like figuring out how to assemble witnesses from signatures, determine which signatures are needed, estimate witness sizes and stuff, that's all really straightforward. I can write like a simple recursive algorithm that, given a Miniscript like this, will just output this data. So if you're a wallet developer, chances are, and if you're doing anything more interesting than like one key, one signer kind of stuff, chances are you've had to deal with script and write a whole bunch of ad hoc code dealing with all of this stuff. And now you can just throw that out. You can just use like the Rust Miniscript library or something. You can take your existing scripts, parse them from script into trees like this, run all your analysis and stuff on that, and it will give you fee estimates. And it will do stuff like they will give you worst case fee estimates. You can tell it like some keys are cooperative, some keys are definitely available, some keys definitely not. Whatever, you can ask it questions like, if I have these keys, is that sufficient for me to satisfy this? If I don't have these keys, like, are these keys necessary? All sorts of stuff, very straightforward, simple, recursive algorithms, okay? So technically, the way I started here, I said Miniscript's a subset of script, right? It says a bunch of fragments. You really don't, like, I don't think the script, I never think about script anymore. I think in terms of these new primitives, these nodes in my trees, and these directly represent the conditions for me to spend my coins, rather than operations in this weird foreign stack machine. Okay, and I have a couple of future work things, but I'm out of time, so I won't go into that. But talk to me later if you want to use this, or if you want to participate, or you want to help out. And that's all I've got. Thanks, everyone.